All right.
Oh, the time didn't change. Kristen just moved it. Oh, nice.
She has to get up there every 5 minutes.
Yeah.
In English. Yeah, Spanish is not good enough to teach physics.
Pretty exciting.
It'll be a good crowd.
Yeah. Several of these people came from Pi. A couple of people here are student volunteers that just came from Pi, and then my roommate came. Very exciting. Very tolerant roommate. Willing to sit through an hour.
Yeah.
Fair enough.
In terms of like showing what an ACC looks like, this is what a kind of audio looks like.
Sure. I have a couple of junker players here. We can start if you want, yeah.
All right. Welcome, everyone, to Valkyrie's dissertation talk. For those of you who haven't met me before, I'm Bjorn Hartman. I'm Valkyrie's PhD advisor. And Valkyrie knew from early on that she wanted to do her PhD in HCI. And that's why she applied to Berkeley in computational biology. And through the inscrutable system, we actually figured out the faculty did the right thing, and her application came across our desk in HCI, and I and others immediately recognized that here's a student with tremendous creativity and potential, and who also cares both about technology and how it's being used. And so HCI was, I think, a good fit, and I managed to convince Valkyrie to switch areas.
All it took was a $3.50 coffee from Blue Bottle.
So Valkyrie arrived here, and she was actually the first student who, with me, ventured into uncharted territory of digital fabrication, which 5 years ago was barely a blip on the radar in our field, and now there are entire sessions, and now even conferences are popping up. So she's truly a pioneer in digital fabrication and interactive technologies for digital fabrication. And had she heeded my advice, she could now also have a faculty job at a place like MIT, where some of her co-conspirators and co-pioneers did very well. But of course, she has her sights set on bigger and more exciting things in the future. And I don't know what those things will be yet, but I'm sure they'll be on the scale of some of the other adventures she's had, such as biking around the entire periphery of Europe over how many months did it take?
6.5.
Or starting, and leading, for what I can tell, if not the Northern American, then certainly the California efforts of the German sport where you hit each other with foamy sticks.
Some of my players are here today, actually.
Yes. So, as you can tell, Valkyrie has many, many talents, and whatever she will do, she will succeed at greatly, and we're just so grateful to have had her attention on HCI for the last 5 years. And so very, very much looking forward to hearing the summary talk of all the great work you did. Which actually, hold on. What she's going to talk about is maybe like 40% of the work that she did over the course of her PhD. So there are many, many other projects that she did herself, and over the past 2 years, she's also advised masters and undergraduate students and basically already acted like a professor. You're not going to hear about that work today, but feel free to ask her about that.
All right. All right, here we go. So instead of waiting until the end, I wanted to be clear from the very beginning that this work was not done by myself, whatever Bjorn's glowing rhetoric says. This is just the people that I've actually co-authored papers with. So this is definitely not everyone who has helped me. All of you in this room have helped me in one way or another towards today, I guess. But thank you, especially to these people. Also, work was not done for free. I have been eating for the past 5 years, fortunately, thanks to generous support from these organizations. So we're going to start like this. Take a look at your hands and think about all the things that you do with them every day. So maybe in the morning, you grab your Bluetooth toothbrush that tracks how long you keep it in your mouth. And then when you get to work, you grab the ergonomic mouse that you don't really like, but that you know is good because you have carpal tunnel. And then when you go home, maybe you sit down and you play some video games on your Xbox. All of these objects and many more are called tangible input devices. So they're ways that we give physical form to digital information. Instead of poking at our flat glass touchscreens over and over for every application, we use a wheel to drive a car, or we use a pair of turntables to control music mixes, or a dance pad to control a rhythm game. Lots of people prefer these kinds of devices because they use them, they get speed benefits or virtuosity, or a variety of benefits from these things. So the difference that I want to emphasize is between graphical user interfaces, which are like a picture of a ball, and tangible user interfaces, which are like the ball itself. So for example, here's a graphical user interface for Fruit Ninja, okay? Obviously the screen is reacting, the cat is interacting with the screen, but you're not really touching it. This is a tangible version of the same idea. So instead of swiping over and over to touchscreen, this guy is like swinging a sword, okay, which is tracked by the arcade system. And this is how he interacts with it. So how are tangible inputs designed? It depends what you're designing. You may be designing an object's role. So this is sort of what place it has in a user's life. Or you may be designing its implementation, which is how you eventually plan to build it when you manufacture it. But in this thesis, we're going to focus on the look and feel prototypes, which is when you're not trying to figure out how you're going to manufacture it, but you just want to know how it looks and how it feels to use. So foam is what's usually used as an early stage thing in this prototyping process. So it's good for form finding, it's easy to cut. You can also add some functionality. So here you see there's a little scroll wheel on the side, so you can scroll the mouse button and see how that feels. But it's not connected to a computer, so you couldn't actually test this with an application. But this talk is about digital fabrication. So the way that digital fabrication gets involved in this prototyping process is that you design a shell like the ones that you see over here, and then you basically have to stuff it full of electronics. So you put little switches under the buttons, you put potentiometers under the dials and sliders, but all of these components that you are inserting, you have to solder by hand. And ultimately your prototypes kind of end up looking like this. So this also hinders iteration, because if we want to change the design of our objects, we have to redo this assembly process every time. So all of the fiddly soldering, et cetera, every time you change the design, you not only have to print a new version, but you also have to reinsert all of these sensors. So we want to make iteration on tangible device prototypes more fast, cheap, and flexible. And my thesis is that digital fabrication can solve this. But how can all these machines printing silly little plastic trinkets help us? So you have a digital model of the physical thing that you're going to get. And it can include different kinds of data. So in this case, this is the ring that I printed for my husband. It includes measurements about the size of his finger, so that I know that once I print it, it will fit on his finger. You can also do more complicated simulations. So this is a design for a clock. Can we get the lights actually, Gustavo? So that we can see a little better the contrast on the screen. So this is a model for a clock. And from the 3D model, we can simulate that the clock will work when it's printed, that all the gears will fit together, that it will keep time properly. The point is that the digital model can tell us something before we have the physical object. And that is how digital fabrication is going to happen. So the basic outline of this talk, I'm going to talk a little bit more about the goal. I'm going to talk about today's fabrication and sensing technologies that we're going to use, briefly go through related work, talk about the 3 case studies that I did as a part of this thesis work, and move on to conclusions in future. So our goal is to fabricate these functional, tangible input device prototypes. The way that we propose doing that is basically fabbing to sense, or fabrication for sensing. So we want to use these digitally fabricated forms to improve functionality and speed up prototyping. We're going to talk about the 3 case studies. Midas is a tool for building capacitive sensing interfaces on non-screen surfaces. Lamello is a technique which generates laser cut and 3D printed geometry and simulates vibrational frequencies so that we can do training-free audio sensing. And finally, Sauron, a tool which automatically modifies the interior of a printed object to allow sensing via a single embedded camera. So, as a quick demo, Midas is this method for automatically generating custom capacitive touch sensors that are cut from adhesive-backed copper foil by synthesizing sensor pads and routing connections from a high-level graphical specification. So Lamello is a technique that uses these passive tine structures, 3D printed at interaction points, like along the path of this slider, that have predictable vibrational frequencies to create passive tangible inputs sensed via audio. And then Sauron, you can see the camera view here. Sauron is a design tool that enables users to rapidly turn 3D models of input devices into interactive prototypes where a single camera senses input. So fabbing to sense, the big idea is using the digital model to make the physical sensing easier. So this is a 3D printed thing. Okay, when I go like this, which is actually really hard with only one thumb, you can hear the sound it makes, right? So it's making sounds as I'm moving it around. And we have a digital model of this. For now, I'm just going to wave my hands a lot and tell you that we can figure out the sounds it's going to make based on this model. So once we know what we're listening for, we can find those particular sounds in a sound stream. And if we interpret and understand how the user is moving the slider around, we can use it as a control. So for example, here, Andrew is controlling these lights. The brightness on them is cued to the slider that he's using. So for the purposes of this thesis, the way that we're going to break down the sensing technique is like this. So there's a user action. There's a transformative mechanism and a material characteristic. And these three things work together to make some kind of sensible change. And once we know what that change is, we pick a sensor that can sense it. Okay, so for example, in this case, the user action is sliding the slider. The transformative mechanism is this time strike. So we move the slider and it deflects the time. Then it slips past the time, and the time is going to start vibrating in place. The material characteristic we have is that it's rigid and sound conducting. So when the time starts vibrating, the whole thing is going to start to vibrate. So the sensible change that we have is this vibration of the whole object, which comes in the form of sound. So the sensor that we choose to use is a contact microphone, which can sense the sound pressure level over time. So user action, transformative mechanism, material characteristic, sensible change, and sensor selection. As far as like the range of user actions, Stuart Card sort of beat me to the punch, 40 years ago. So I'm not going to talk about this. You can read his work about that. And he also talks sort of about these transformative mechanisms that we can use to change those into things that we may possibly be able to sense. What I want to focus on is these three last parts, the material characteristic, the sensible change, and the sensor selection. But first we're going to talk a little bit about digital fabrication so that we have an idea of where we're going. So the two main types of fabrication machines are subtractive machines, where you take basically a material blank and you insert it into the machine. And then it sort of subtractively, it cuts away parts of it so that you end up with the shape that you want. So here in a laser cutter, you put in a board, and then the laser is basically vaporizing a part of it so that when you pull this out, you'll have your gear shape. And you can also do this with things like CNC mills, which work with materials like metal, or with vinyl cutters, which work with essentially sticker sheets. There's also additive manufacturing, which is what everybody thinks is so cool right now. And this can range from 2D things like inkjet printers to 3D things like 3D printers, which essentially the way that this works is you don't have a material that you're cutting apart, but instead you have a material feed that you're slowly building up into a final design. So what are some material characteristics that we can get from these machines? The particular material characteristics that we end up with can lead to ways of generating or transmitting the signals that we're generating for sensing. So the four sort of most popular digitally fabricatable materials are plastic, metal, wood, and paper. So that's what we're going to focus on for this talk. And as you can see, there's a lot of different characteristics that we looked at. So we looked at how much light these things let through. They can be transparent or opaque. We can have multiple colors in some cases. We can do rigid and flexible parts of the material. And then they also behave differently with respect to like electrical signals. So they can conduct them sometimes or work as resistors. And then when we combine the materials with different fabrication processes, we can also get geometric characteristics. So for example, a 3D printer can print 3D objects, as one would hope. Some of them can also blend different materials together in the same print. Some of the machines only work with particular types of materials. So. And then there's some kind of sensible change. So this really heavily depends on the first three things, the user action, the transformative mechanism, and the material characteristic. But you can imagine a bunch of examples. So a change in electromagnetic signals, which is what we're seeing here, a bump in capacitance, a sound, visible motion, a change in pressure, change in moisture. And then you have to pick a sensor that's compatible with that. So we use sort of the classification from the Modern Sensor Handbook of force, strain, tactile sensors, humidity, moisture, light detectors, etc. And then we end up with this big table, which is in my thesis, if you would like to spelunk into that document. But the three places in this space we're going to look at are Midas, which, as I said, does touch sensing, Lamello, which does audio sensing, and Sauron, which does vision sensing. So there's been a little bit of work with digital fabrication on topics sort of related to this. So for example, in fabrication for interaction, here they've printed a flexible, hollow object. So when they push it, there's a pressure sensor down here, and this is registering the changes in pressure. And so you can get different interactive characteristics as you crush these little buttons. FlexiBend, basically you fabricate an object so it has this special track, and you put the sensor into the track. And then as you move things around, you can see the sensor readings are changing as he moves those two objects. And then you can use it as a input device. I have to say the question I get most about my research when I say I do 3D printing work is, did you know you can 3D print a gun? So there you go. And then on the other side of interaction is output. So this is like printed optics. They basically print these hollow, well, they're not hollow, these clear tubes that can bend light through them. So you can put it on top of a projector, and then you end up with little screens that don't look like a projector, but instead can be embedded in 3D objects. But the thing we're really interested in here is making the digital model work for us. As I said, if we have some knowledge of the digital model, we can do simulations before we have the object. So models for simulation, there's also some work there from the graphics realm. So this is a project where basically they can hollow out parts of the model to create the right center of gravity so that when they print out the object, it will balance in a way that they want. And then this project, they basically blend different types of flexible and rigid materials so that they get a bending, a flexibility profile that matches a specification. So that they have a printed flip-flop and a regular flip-flop, and they put force on them to see how close those flexibility things match up. But in this thesis, we want to combine fabrication for interaction with models for simulation. And we want to make it fast, cheap, and flexible. So we're going to move into 3 examples, Midas, Lamello, and Sauron. So we're starting with Midas. This is sort of the most familiar touch interface that probably all of you interact with every day. It's super easy to develop for because capacitive touch and output are co-located on the screen. So developing for this is essentially a software problem. But if we want to include touch input in places that are not the screen, it becomes a lot harder. So if we want to do it on the back of the device so that we avoid having our users' fingers covering their screen, or if we want to do it on the mouse where there's no screen at all, it becomes a lot more complicated. It becomes a hardware problem. So we wanted to look at this difference between touch hardware prototyping and touch GUI prototyping. So the way Midas works is users design touch areas. We have a drag and drop sensor editor interface that I'll show you. Then they fabricate those sensors using a vinyl cutter. They'll assemble the sensors by essentially sticking them onto the object that they want to make interactive. They can define events in the sensor editor. So essentially tell the computer what they want to happen each time somebody presses the check mark or the X or the arrow. And then they can test out the interface. So here's the sensor editor interface. It allows drag and drop. You can resize things, rename them. In this case, we have a couple of stars and a slider. You can also add obstacles, which we're going to do here. So in this case, we say, okay, I know that it's going to give me a bunch of traces, but I don't want the traces to go over my camera and obscure it. So once we've done that, this tool is also where we can tie interactions to actions. So in this case, we want the star, we called it starred emails, so we want to record an interaction where it looks for our starred emails. So we have our, our inbox over here, we click the star, and now it's recorded that action. So every time it sees somebody press the star button, it's going to look for starred emails. So we replay the action to test it. So how does this fit into our sort of framework? So the action we want to track is touch. There's no transformative mechanism in this case because all the parts are essentially still. The material characteristic that we need for this is conductivity. We're going to sense a change in capacitance using a capacitive sensor. So after the designer finishes their sensor design, they generate the things to be fabricated, and this is an example of that. So you can see this is how the traces go around the obstacle. The camera would be right in the middle there. And then Midas also generates these instructions for them, which tell them how to put the object together. They can fabricate these things on a vinyl board. It's not quite that loud. And then they stick them onto the object. And following the instructions, they basically hook it up to the sensor controller. We also generate essentially mask layers so that we can avoid sensing touches on the traces, and we instead only sense the touches on the exposed areas, which are the buttons and sliders that we have. So how does it work? These are sort of the common inputs that we support with Midas. So we have buttons of various shapes. You can input any shape you want. We have a discrete slider. We have this continuous slider, which basically works on differential capacitance. So as you move across it, each of these interdigitated pads is going to sense a different capacitance, and we can interpolate where you are along the slider. And then we also have a two-dimensional pad, which lets us address more space on a grid using fewer sensor lines. And then we route these using the breadth-first circuit board algorithm. So eventually we have a shape, and we can make it with a variety of different processes. So in all the examples that I show, well, most of the examples I show here, we use this vinyl cutter with conductive copper tape. And then we can also do it on a circuit board. But we could also do it, this is indium tin oxide coated plastic, which is also conductive. So it's really the material characteristics that matter. It's just the conductivity. So we can support different types of board. So this is clear. The circuit board is rigid. The stickers are flexible. As long as we have the conductivity, doesn't matter what the material is. There's also, in additive manufacturing, they're working on 3D printers that can print conductive stuff. Inkjet printers can also print conductive traces. So we can use any of these processes to generate the sensors once we've designed them. And then the microcontroller that we use is this. So it's got, this is a capacitive sensing chip. On the back of it, which you can't see, is the connection to the computer. And then it's got the wires that come off that you connect to your sensor traces. And actually recently, Mitchell very kindly, where's Mitchell? He very kindly fabricated me this beautiful new board, which works way better. And it has Bluetooth, so it can talk straight to the phone. It doesn't have to hook into the computer. So why is digital fabrication so good here? So because Midas is routing the traces, it can pre-program the microcontroller, and it can ensure that the assembly is done correctly. So Midas routes this thing, and then the designer follows the instructions and connects the rainbow wires to their traces. But since we generated the routing and generated the instructions, we know how the sensors will line up. So we know that the check mark is going to touch the brown wire, and the X is going to touch the red wire, and the arrow is going to touch the orange wire, blah, blah, blah. So we can pre-program the microcontroller to attach our recorded actions in the right way. We can use we end up with these numbers. We can use the check mark to check the email, the X is deleted, etc. But when you tape all the wires on, things can still go wrong. The wires could be too close together, or the tape could not be sticking correctly. But the cool thing is the digital model also helps us here. So there's basically characteristic ways in which humans interact with things. So for example, if we see a signal that looks like that, where the check mark is being pushed and released dozens of times a second, it's pretty likely a human is not doing that. So in that case, we assume that the connection has just been done incorrectly. For example, if the tape is not stuck on, then it might just be floating above the thing. There's also another case where maybe a human presses something, and then they just wait, and nothing happens for a long time, and then they release it. And in that case, that's also not a very likely interaction. So we can say that, maybe the traces got too close together. Maybe, they're slightly too close here, and the X is interfering with the check So we can pop up a warning to the designer and be like, yo, we don't think you did this quite right, maybe look at it again. Of course, there are limitations to this technique. So stickers are really hard to apply, even on flat things. So this makes Midas pretty good for flat things and unfoldable things with flat sides, but like a sphere, not really going to work with this technique. And also it is kind of a pain to sort of weed out all the parts of the sticker that you don't want. But again, because it's just the conductivity that matters, we can change the manufacture technique for the sensors and still have our objects work. So is this fast, cheap, and flexible? So we did a small user study with a few users in our lab, and they all managed to design music players with Midas in under an hour. So that seems to indicate it's at least fast to learn. It's cheap. The materials, I mean, a sheet of this copper stuff is like $8. The vinyl cutter that we used was like $200, so no big deal. Plus, you can reuse the microcontroller every time. You don't need a new sensor every time that you make a new object. It's flexible, so not in terms of the material, but in terms of the technique. It allows for many different things. So here's a slider that controls a Pong game. This is a postcard that plays music. These columns over here. We made a papercraft pinball machine that controls actual pinball. It's not limited to computer-based prototypes, so when it's interpreting these sensor inputs, it can send them, over the internet so that we can have something based on our phone. Or as I showed, we can also talk directly to the phone. So here you can see this is responding every time I touch the sensor. Okay, we're going to move on to Lamello. Andrew is my beautiful hand model for this project. So Midas-powered touch interfaces can be really powerful, but there's nothing quite as satisfying as physically manipulating mechanisms, like sliders on turntables and volume knobs on these things. But this is inherently three-dimensional and not two-dimensional. So we're going to need to move into a third dimension in order to do this. So this is our slider design. And as I showed before, it makes sounds when it moves. And that's what we're going to use as our input. So the way Lamello is going to work is that it generates geometry, and then it plugs some characteristics of the geometry and the material we're going to use into a model which it uses to predict frequencies. Then we go over and we fabricate our object, and finally we can test it. The actions we want to sense here are pushing, sliding, and turning. The mechanism we're going to use is tines. We need this rigid sound-conducting material, as I said. We're going to sense a change in vibration in the form of sound, and we're going to do that with a microphone. So again, just briefly what we talked about at the beginning. So when we slide the slider, it's going to hit this tine. It's going to slip past. The tine is going to start ringing up. And then because we have this sound-conducting material, the whole thing is going to ring. And the change that we're sensing is this vibration, and we use a microphone which can get it out for us. So we put tines in 4 different kinds of tangible input components. We did buttons, we did direction pads, we did dials, and sliders. And basically the way that each of these things work is that they're printed onto the interaction points. So as you move this joystick around, the wings basically on the ball are going to strike these tines as they move by. And on the dial, there's a little knob on the dial, and as it twists around, it's going to strike the tines arranged radially around it. And the cool thing is that, like I said, Lamello is a sensing technique that doesn't require training or initialization once you print it. It just needs the digital model as input. And the sensing is done via passive audio. So all you have to do to sense is you clip on a contact mic. And this is an example of what the contact mic is hearing. And then using the digital geometry, the software can pass the sound on to interactive programs to use it as input. How is digital fabrication helping us here? So I said that Lamello can predict frequencies to listen for based on the model. And how does that work? So we have the model that we're using, and each time has some geometric characteristics. And the ones that we need are the breadth, the thickness, and the length of this time. There's also a material component to the model that we use. Basically, we need to know how heavy the material is and how quickly it'll spring back into place, because these two things are going to tell us how fast it can vibrate. So the two materials we tested out were ABS and Delrin. So how do these things go together? Fortunately, mechanical engineering already tells us how they go together, so here's the height and length of our time, and then the Young's modulus and density of the material that we're using. So these things, essentially we just plug them in, and out magically comes the frequency that we're going to look for. But there's sort of a question about this with 3D printing. So if any of you have ever 3D printed something, when you look at it, it looks kind of like this. And that model from mechanical engineering assumes a uniform cantilever. So we needed to test if this would actually work with our printed objects. So to validate the model, we ran predictions on data from the model of a cone that we printed. And then we used using the breadth, height, and length. And then using the actual printed model, we measured the breadth, height, and length because of course they don't come out perfectly from the printer. And we did the same predictive task again. And then we actually measured what we saw. And so these things ended up lining up quite well. It was interesting because the Young's modulus, the flexibility of the material, depended on a lot of things, including what color it was printed in. So that was a little irritating. But the mean error of our model over all the different objects we printed was certainly within the realm of making sensing feasible without training. So once we know what we're listening for, we have to figure out what it is that we're hearing. So we have, these are two different tines being struck. And if we look at them, like they're shaped a little differently, but it's not clear what the characteristics are. So instead of looking at them in the time domain, we look at them in the frequency domain. So what we're looking at here is these are low frequencies and these are high frequencies, and time is moving this way. So we have basically teeny tiny blocks. The yellower a block is, the more of that frequency we're hearing. So if we look at it in this way, we can sort of start to see a difference. So the sound that we're seeing has basically two parts. So there's a transient which comes at the beginning, which is a broad activation across a bunch of different frequencies. And whenever we have a striking sound, we get the transient first. And then we get the steady state, which is where the time is just sort of vibrating on its own, and there's not the striking sound of the things actually hitting together. So we want to take a slice of time after the transient so that we just get this steady state. And then if we look at these frequency distributions, it's pretty clear that these are different times. So to figure out which time we have, we look at the Fourier transform, the frequency analysis basically of the sound, and then we look at it around each of the frequencies we predicted. So in this case, we predicted a frequency that was here, and one here and one here, but we give it a little bit of leeway because you saw there was some error in our model, so we just look at sort of the sum of stuff that's around those predicted frequencies. And in this case, we see the most activity in this frequency, so we say that that's the frequency. So there's a bunch of limitations of this technique too, of course. It's got layer-sensitive durability. So when you 3D print something, it basically lays down layer by layer by layer. And if you print the tines so that they're bending across layers, they just break. It's, that's how 3D printing is. So you instead have to sort of print them, down in the bed. Also at the beginning, our accuracy was not that good. So we went through and we struck all of our tines 10 times, and we looked at the precision and recall, which is basically, did it pick the right time, and did it pick the time at the right time? And okay, for those of you that aren't in HCI, these numbers are really bad. So we looked at, we'll just stick with that. So we looked at what was going on. And basically what's happening is that we're just doing awfully. Once we get above 2,000 hertz for the frequencies, we just we're not getting anything. So we had to adjust. And this is basically because, as we saw in the previous frequency pictures, lower frequency times, there's just more energy for a longer time here. Whereas in the higher frequency one, this is the energy we're looking for, but there's not so much of it, and it ends earlier. So basically our classifier just didn't have time to make a good prediction on this. So we instead repeated the tests with the 4 times that were performing the best, and we got these much more reasonable numbers. And the plucked Delrin is especially interesting because it's not a 3D printed material, it's a laser cut plastic. And it outperformed our printed materials, which was kind of cool. And since we don't have quite so many frequencies to work with now, we looked at different ways of encoding information. So you can do a linear thing, but with the same number of tines, you you can also interleave them so that you get higher information density, and there's basically a larger code space. Anyway, another limitation of this technique is that the interfaces make noise. Okay, so some people might find this really annoying, but I would like to think that eventually it could be really nice. So this is a lamello phone, which is what the technique was actually named for, that essentially works on the same, you pluck a tine and it has a nice frequency. So is the technique fast, cheap, and flexible? So we have code-based generation of tines, so designers don't have to worry about that. The frequency prediction is essentially instant once we have all the model inputs. And not to mention, as I said, we can do it with laser cut tines, so we don't have to wait necessarily for the 3D printed tines to come out. Super minimal assembly. Now the object is ready to be sensed. It's cheap. Of course, the materials are cheap. Plastic is cheap. It's flexible. We used it in all different kinds of different input devices. And as I said, we can also do it wirelessly. So this was sort of an informal test, but we don't have to use a contact microphone. In this case, we're just using the microphone in the laptop. Okay, Sauron. So where Midas dealt with touch and Lamello dealt with sound, Sauron is going to deal with vision. The action that we're looking for is physical manipulations in the same way of Lamello. The mechanisms that we have are spatial mechanisms, so they're going to be moving around. We need two-color material for this technique, and the change we're going to have is visible motion. So when we have colorful things moving around, we see it move, right? And of course, the best way to sense visible motion is with the camera. So how does that work? We're going to design the 3D model, we're going to print it out, and then we're going to screw in a camera. And then the camera is going to, look at what's going on inside. And after we register the components with the computer vision system, then we can use this as an input device. But just putting a camera inside the 3D model is not going to be enough. You can see here that from any angle that we look, not all the components are visible. So in this case, we have all the buttons around this object, and we can't see them all from one place. They're up in the corners, or these are even sort of behind the camera. So when he's designing his object, the user is going to create a CAD model into which he's going to put a virtual model of the physical camera that he'll use for sensing. We can check the visibility of components at that time to let the user know, okay, those two in the front, we can already see them, but the other four components on the sides, we're going to have to do something to be able to see those. Then Sauron takes over, and it basically automatically does these modifications to the components. We print the model, we start tracking, and then we can test them. So in our work with Sauron, we basically came up with these 7 different input components that were useful in our process. But this library is extensible. So the only thing that you need to be a sensible input component is to have an idea of what area you need to be able to see in order to do the sensing. So in this case, for the direction pad, we need to be able to see all 4 of these little legs. For the button, we need to be able to see its tail, etc. The dial, we need to be able to see the whole bottom so we see as it moves around. But even without building a new component, you can still modify these so that they work on the same sensing principles, but have a different form factor. So the dial can be smaller and peaked to become a volume knob, or we can stretch it out and add little ridges so it's like a scratch wheel. But these all have the same sort of profile, so that we're looking for this little knob on each one. So as I said in the other projects, why do we need digital fabrication here? So the action that Sauron is performing is it's modifying the model so that one camera can see all of these parts. This is where we insert the virtual model of the physical camera we're going to use. We know that we're going to screw it onto this point, so we just insert it there. And then, as I said, the goal is to modify it so that we can see all the components. In this case, we're doing the quick check. So by essentially intersecting our components with this is the field of view of the camera, this big boxy thing. We can see that these components are already inside the field of view, so we don't need to do anything. But none of these 4 components intersect that field of view, so we're going to have to do something different from them. So what can we do to help out these components? The simplest thing we can do is just essentially extrude them. So if we have a component that's over here, the camera can't see it, we can just stretch it out until the camera can see it. This is really good when you have a bunch of components that are not around corners. So this is a dodecahedral ball of buttons, and basically we can just stretch all of these buttons legs out until they're in the field of view of the camera. But what about more complicated objects? So this button, if we try to extrude it, essentially it's going to run into the wall. And it's never going to reach the camera's field of view. So we have to do something fundamentally different here. So we start by casting out rays of what the camera's going to see. So this is like basically a ray tracing thing. And then when a ray meets the side of the component, we have to figure out what's going to happen. So, you know, we have a ray, we have a normal, and then we can calculate a new ray that's its reflection off of the inside. So basically, Sauron looks for all of these rays that once they reflect off the object, can see the component. And what that means is that at that place where they can reflect to help us see the component, we can put a mirror after we print. So in this case, for the game controller example, you know, this camera, if we put mirrors in these two places, it'll essentially bounce and it'll see those objects in the back. And here you can see it in the printed object. So this would be the camera's point of view. Here's our little mirror that we put in and the button on the back of the controller. And here is essentially a video from the camera where you can see in the reflection of the mirrors the buttons moving. But one thing about all these components is that they move, right? So, I mean, as you can see, so we do a little bit more simulation to make sure that these objects are going to be practical to use. So first we have to, you know, make sure that if we move our components around and we put extrusions on them, they're not going to knock into each other. So if they do, you know, we take the extrusion off. Users would get kind of annoyed if we modified their things and then the controller didn't work anymore. So also when they move, they might move out of the camera's field of view. So as we're moving the slider along this track, we detect that it's outside, and so we have to stretch it out a little longer. And we move it back to make sure it's not going to hit anything. So this is the modified game controller. Basically, for these two buttons, we've taken them and we've extruded them out into the camera's field of view. And then for these two, as I showed, we're going to input the mirrors there. So we send it to the 3D printer, and when it comes out, I told you we need 2 colors of material to help with our vision sensing. So for the first time that we did this project, basically when it came out of the printer, I took a permanent marker and I marked it up. But now we have Jacobs, hooray, so you can actually print this right into the model. So this is a multiple material printer that can print black and white in the same print. So this is all integrated. Yeah, it just costs 10 times as much. Exactly. So most of them you just have to put a dot. But depending on the sensing algorithm you're using, you may need to put, you know, more. So in this case, the trackball uses optical flow, so we need a bunch of dots so that, you know, one is always visible. And then even Jacobs doesn't have a printer that can make specular materials, so we do have to glue in the mirrors when we're done. And then when the glue dries, you know, basically we screw in the camera. And then the interactions are sensed through computer vision. So we'll just talk really quickly about how that might work. When we know where the components are, we use different sensing algorithms for each one. So if this is the button, basically if we see the button move, we know the user must have pushed it. Okay, so that's very easy. And then other components work on different techniques. So here we have a scroll wheel, which works on optical flow, so we watch the way in which these rectangles are moving up or down. The trackball also works on optical flow, so we watch how these dots are moving in the XY grid, and that tells us how the user's moving it around. And then also the direction pad, it actually looks at the deformation of the blobs. So as you see it moving, the dots are sort of changing size and they're shearing with respect to the view of the camera. This technique also has limitations. It doesn't work very well for shallow models. This is the most particular problem. So we have to have a camera, and you know, if anywhere that we put a camera in this button, for example, would be really hard to see because there's this super skinny arm that goes out to it. So, you know, while we could line the entire inside of the model with mirrors, for right now we only use one mirror bounce. So models like these, where it's just hard to fit a camera in, are hard to sense. Is it fast, cheap, and flexible? Actually, everyone who participated in this study has graduated, so I cannot call them out. But we did another quick user study, and some of the brilliant mechanical engineers in our lab were able to create Sauron sensible prototypes within an hour. It's cheap, as I said. You know, plastic is cheap. If you go the permanent marker route, it's cheap. If you want to print it all in one go, slightly more expensive. The camera itself that you're using to sense could be expensive, but again, reusable across prototypes. And then flexible in terms of different kinds of things that you can use it to sense. We basically went on GrabCAD and we found everything that was tagged with interactive or controller. And we tried to figure out if they'd be able to be used with Sauron. And it turned out that 7 of the 10 models we tested would have worked, even though those designers obviously didn't create them with this technique in mind. We also created some examples. Here's Bjorn testing out our DJ mixer that's connected to this commercial DJ software in the background. The volume and cutoff filters are tuned to those knobs. I already showed the game controller. And then we also made this sort of ergonomic mouse. So what do you do in the future? The sort of assumption of all of these different techniques is that we have a single fabrication machine that's creating one prototype at a time, which is hand optimized by a designer, and that uses a single sensor to do sensing. So what if we use multiple machines? We could speed up our fabrication process, or we could get different kinds of material properties using these different machines in concert. Or we could create lots of prototypes. So the cool thing about digital models is that once they become digital, they're essentially like code. So we can version them, we can share them, we can unit test them in code. And then there's sort of the advantage of some 3D printers can actually print a bunch of things at once. So in a powder bed printer like this, it's sublinear scaling in time. So you can print 10 of these things for only slightly more than the cost of one of these things. What if we have the machine optimize our prototypes? So right now, the designer has to be like, okay, I think I want it to be about this size. I want the buttons to be here and here. But if we want to design for particular users, we can measure their hands, right? And we can say, oh, like Craig has really long thumbs, so he can have buttons that are way out there. Or like Sarah has really bendable pinkies. That would be kind of a cool skill. So she can actually, move the things around in a different way.
Donald Trump has small hands.
Donald Trump has he's got to have a little controller there. Let's not talk about what else is small. Okay, but using the computer, we can easily get a lot of measurements by just sensing these things, and we can use them as just inputs to our models. And finally, what if we use multiple sensors? So sort of your cell phone is a big sensor brick, right? It's got an accelerometer, it's got capacitive sensing, it's got a camera, it's got a microphone, it's got geolocation, it's got magnetometers, all kinds of good stuff. And this preserves the idea that we only want to snap on one piece at the end. But by leveraging multiple sensors in the same object, we could have more precise or more flexible kinds of sensing. So to conclude, as computing is moving off the desktop and into the world, we're seeing an exploration of a bunch of different varieties of input devices that are designed to sense new and specific kinds of input. These devices necessitate a new kind of prototype that doesn't fully rely on software, but which allows for functional physical objects in a fast, cheap, and flexible way. I describe digital fabrication as a way to achieve this by linking a digital design to a physical completed output. So the projects that I talked about are intended to shorten the drudgery sort of associated with this iteration process. Midas does sensor routing and uses the knowledge to pre-program the microcontroller and also ensure that the assembly is Lamello used 3D geometry to predict time's resonant frequencies for audio sensing, and Sauron manipulated an object's digital model so that a single camera would be able to sense all the input devices. Hopefully, and also it helps keep the pieces from colliding in the hands of the end user. So the suite of tools in the space that they explore will hopefully empower designers to invent and hone designs for the future of interaction. So speaking of honing, in Asia, there is this sort of technique of like marking transitions in one's life, which is cutting off the hair. So I wanted to do a user study that Bjorn did not know about this. So in this case, it was an n=1 user study. It was longitudinal, over 5 years. And the question I was looking at was, how can we effectively visualize a PhD? And I wanted to collect periodic reflections on this visualization. So the user, of course, was me. This was me at the beginning of my PhD. My mom is not happy. So since that time, basically the hair just kept growing. So, oops, oh my goodness, sorry. Since that time, the hair has just kept growing. So 2 interesting results of this are, it made people scared of me. It is hard to make friends when you look like a serial killer. And it was poor personal branding. So for example, I met Jan at my first whist, and then when I met him at my second whist, the first whist, hair is this long, second whist, hair is this long. Jan says, who are you? So,
Guys, you know?
no, I totally get it, it's fine. So, I wanted to end my thesis by sort of making this visualization more interesting. This is thanks to the help of my wonderful roommate. I hope to God it works.
Watch out for the ear. Not the ear.
No, I'm not going to get the ear. Oh, jeez.
I'm not sure if you can
I don't know if it's sharp enough for this. Is it going through?
I
I can hear it only sometimes. Oh, I was hoping
It's not
this would be so
supposed to be
dramatic.
easy, right?
Yeah, that's what the videos made it look like.
It's a better user
getting
interface.
through, yeah.
Is it, how far are we? Oh, we're like almost done.
Advisor
yeah,
needs to
yeah.
help.
Definitely cutting.
The advisor comes to help.
Oh, are you gonna help me?
Very careful.
Worst idea.
80% done.
About 2/3.
80% done.
2/3. That's how I feel about my PhD. So my hope was that I would just go like whoosh, and then I would set it on the table in front of Bjorn, but clearly this is not going to happen.
Also a metaphor for a PhD. It takes a lot longer than you expect.
And who are you?
All right. Thank you for listening to me. That was great. Congratulations to Bjorn on his first PhD.
Yes.
Yes. You set a high bar that Peggy will now have to meet in a couple of
poor
months.
Peggy.
Oh, there was one final anecdote, and that is there is this rule that apparently you cannot graduate from BID until you get a best paper award. And we got the wrong reviewer twos for our project, right? We were sure that Soren was on track, but no such luck. So I was really thinking that we're going to have to keep Valkyrie here for another 2, 3, or 5 years. But no, just this week at Kai, the project she advised that Alden and Michelle spearheaded won the Best Late-Breaking Work Award.
Yay!
And so we'll let that count, and with that,
Thank you,
yes,
thank
you're ready to graduate.
Great. All right. Lights on. I think all the pizza and cupcakes are gone, or I would invite you to have some more.
So where are you going next?
Well, in about 2.5 months, my lease is going to end, and Evan and I are going to get on our Vespa and drive to Toronto.
Yay.
That's where I'm going next.
University to DC or?
No, we're going to do a startup. Actually, I want to talk to you about it because it's educational technology. So, yeah, I'm very, very excited to explore a different area for a little while and see what that's like.
But tomorrow, she's getting a haircut.
Not maybe
I just want to say thanks for being such a great voice and researcher to lead the HCI effort. You know, you've really been a great spokesperson for
Thank you.
HCI at Berkeley, and it'll be sad to see you go, but you will always resonate here with lots of energy from your research. So thank you for your contributions to the community too.
Thank you for all of it. Cool.
Awesome.
So did anybody require completion time for that?
On the hair? Oh, I think my sister recorded it. Oh no, actually you were supposed to record Bjorn's reaction.
It's okay, we have documentary evidence.
Almost everyone
so we
in
can
this
figure it
room
out
knew
later.
that was going to happen. So, yeah.
New transcription, right? Yeah. Closed captioning cuts hair.
Thank you, everyone.
Yes.
Still good. Gentle sawing.
Gentle sawing.
Future students assume